So this is after the exam. I asked everyone to take a look at 8.1 and 8.2, but you're not ever going to have to do 8.1 and 8.2. 8.1 and 8.2, if this were a bigger class, if this were a trigonometry class, and we were going to spend a lot of time on trigonometry, we would do this. And in fact, sometimes we have, and it ends up being a headache, and no one likes it, and everyone gets confused. So we're just sort of skimming past it to get to other things. The idea is that you could extend what we know about trigonometry for right triangles, to bigger angles, angles bigger than 90 degrees or bigger than 180 degrees, and less than 0 degrees, going backwards or forwards, all of those other angles. That's meaningful and useful. They end up being the same sines and cosines and tangents that we were looking at before. They just have different signs in different quadrants. So over here, the cosine values would be negative and the sine values would be positive. Down here, the cosine values and the sine values would be negative. Over here, in the fourth quadrant, the sine values would be negative and the cosine values would be positive. But you don't have to care about that. The only reason I want you to look at it is just so you recognize that when we get to graphs later. Skim this if you want, but don't pay it much heed. Same thing with 8.2. They're looking at, if this were a beefier trigonometry class and we were going to spend a lot of time, we could look at how to evaluate trig functions of all of these weird angles by looking at reference angles. You're not going to have to do that in this class, for me. Here's another interpretation. We can think of sines and cosines and tangents and secants and cosecants and cotangents in terms of points on a unit circle. Instead of thinking of right triangles, we could think about points on a unit circle. And that actually has a more natural extension to these other values, which is nice and useful, but we're not going to fool with it. We are going to take a look at, from that quick skim, I hope the one thing that you observed was the sines and cosines and tangents were exactly the same as what they usually are, except in some quadrants they're negatives. I do want to look at, we actually looked briefly at radian measure. I talked about radian measure and calculators when we were looking at decimal degrees and degrees, minutes, and seconds. I want to think about radians in a little more, with a little more care, a little more investigation. Radian is a measure of an angle, but radians are defined so that they're exactly the same angle measurement as the length measurement around this circumference, which is cool. Degree measurement is really an accident of having a 360-day calendar. And honestly, we don't even have a 360-day calendar. We have a 365-day calendar, but 365 is a hard number to work with, so 360 is easy to work with. That's kind of artificial. If we meet aliens, there's no reason to ever expect them to measure angles in degrees. On the other hand, radian measure, they might call it some other name, this relationship between angle measurements and length around the circle, length around the circumference, if you took a circle with this fixed radius and you took a piece of rope that length long and laid it around the outside of this circle, that angle that it marks out is exactly 1 radian. And if it's a big circle or a little circle, it doesn't matter, any circle, that angle is going to be exactly the same. That's handy and useful. Here they marked out 1 radian, 2 radians, 3 radians, 4 radians, 5 radians, 6 radians, and a smidge more. This ends up being twice pi radians, 2 times 3.141592653589979. 2 pi radians is 360 degrees. We looked briefly at conversions before. We'll do some more conversions again, but that's straightforward. If you remember that pi radians is 180 degrees, or 2 pi radians is 360 degrees, then you can multiply by pi radians over 180 degrees to convert from degrees to radians, or you can multiply by 180 degrees over pi radians to convert from radians to degrees. So here are some conversion problems. Turn this into radians, turn this radian measure into degrees. It's worth pointing out, even though this says RAD for radians, typically we don't write anything at all for radians. The special symbol that tells you that a measurement is in radians is if nothing is written. If we're talking about an angle measurement and there's no special symbol for it, that means it's in radians. Down here, radians have no units, and radian measure amounts to measuring angles in terms of real numbers. So often this wouldn't even be written as 3 pi over 4. Radians equals 135 degrees. It would be 3 pi over 4 without saying this. And if you're not saying anything, if you're not writing anything, that means this is measured in radians. Here, no indicator of the angle measurement means that it's measured in radians. A lot of calculators will do conversions. A lot of calculators will do trig in radian measure or degree measure, whichever you like. You can do the work in whichever way you prefer, depending on your calculator. Some calculators have a little subscript if they're talking about degrees or if they're talking about radians, D or R. Some calculators don't display anything here but have a little note up in the corner to tell you what mode you're in. Some calculators don't easily tell you what mode you're in, but you have to figure it out yourself. I recommend doing something like taking the sine of 90 degrees or 45 degrees, and if it ends up being what you expect it to be, then you know you're on track. The tangent of 45 degrees is going to be 1. The sine of 45 degrees is going to be 0.707. I'm sorry, of 45 degrees. And if that's in radian measure, then it's going to come out to be a weird number, and you'll know, hey, wait a minute, I need to fix that. So we could certainly do computations either by doing them in radians or degrees, or converting back to a more familiar one and doing it there. But I want to look at why the heck do we care? I mean, yes, the fact that aliens probably won't use degree measurement and they might measure things in radians or something, maybe with a different name, but structurally the same as radians. But meeting aliens isn't the biggest reason for doing things. Radian measure translates naturally into a lot of applications. And so we'll look at a handful of applications. Velocity of an object undergoing simple harmonic motion at the end of a spring is given by this formula, where this is just a constant multiple, and this angle is measured in radians. So if we just store this value and have this calculator in radian mode, then whatever this is, I can just plug in and this is one where we've got all 4 quadrants that we're not really going to fool with, although we will look at some graphing things later. Don't worry about reference angles. Don't worry about reference angles. Because radian measure was defined in terms of arc length, there's this natural connection. The length of an arc is the angle measured in radians times the radius. That's awfully handy. And that doesn't work nearly as naturally in degree measurements. In degrees, you'd have to convert it back to radians and then do it that way. Whereas, find the length of an arc on a circle of radius 3 inches, for which the central angle is pi over 6. All you have to do is multiply this angle by this radius, pi over 6 times 3. And this is the length of the arc. And if I want a decimal approximation for that, I can get one. That's pretty quick and slick and easy. And that would be substantially more of a bother if we had to do it in degree measurement. What made this nice was this was written in radian measurement. Pi over 6 is 30 degrees. If I said find the length of an arc on a circle of radius 3 inches, 3.00 inches, so 3 significant digits, for which the central angle is 30 degrees, there's no immediate connection between 30 degrees. Yeah, I'll get to you in a minute, Matt. We've got about 5 minutes of class left. Some more examples. The longitude lines on the globe or the equator are great circles, and we could measure arc length around those. A nautical mile is the length of arc along a great circle of the Earth for a central angle of not 1 degree, but 1 minute, 1/60th of a degree. So this is the traditional definition, and this is the modern definition. And the question is, if those are the same thing, what are they assuming for the radius of the Earth? The arc length is radius times angle in radian measure. So if we solve for the radius, that's arc length divided by this angle in radian measure. This was actually written in degrees, so I have to convert it into radian measure and get a computation. In fact, the Earth isn't a perfect sphere, and there are lots of variations. Here's another example. The area of a sector of a circle is 1/2 the angle measurement in radians times the square of the radius. That's proportional to the area of the entire circle. That's really whatever this angle portion is of the whole thing, of the entire circle. But if this measurement is in radians, then this naturally translates easily. So here's a pie chart showing that 17.5% of high school students send at least 200 text messages per day. On a pie chart of radius 8.50 centimeters, the central angle is going to be 63, 17.5% of 360 degrees. The area of that wedge, of this wedge, is if I convert this angle measurement into radians, so they converted this angle measurement into radians by multiplying by pi over 180. 63 degrees is going to be 63 times pi over 180, that many radians. 1/2 that angle in radian measure times the square of the radius gives me the area of that pi wedge, which is pretty cool. If we do it in degrees, it doesn't translate. If you just multiply 63 degrees times 1/2 times the radius squared, that doesn't give you the area. But if this measurement is in radians, then it does. That's handy. Here's one more example. Angular velocity related to linear velocity. So if we have something that's moving around a circle, the linear velocity is just the angular velocity times the radius of the circle, which means that if we know any two of these values, we can figure out the other one. If this is measured in radian units per whatever time we're interested in, radians per second, radians per minute, radians per hour. If this is degrees per second or degrees per minute, then we have to convert it to radian measure in order to do this. So as an example, someone's on a hang glider moving in a horizontal circular arc of radius 90.0 meters, so 3 significant digits, with an angular velocity of 0.125 radians per second. The person's linear velocity is, all I have to do is multiply that angular velocity in radian measure per second by the radius, and that gives me linear velocity. That's pretty cool. If this were measured in degrees per second, it wouldn't be as natural, and we'd have to convert and do something else in order to get there. This is the same problem. I'm running out of time. This is the same problem with a satellite. This is essentially the same problem with pulleys, where we've got velocity, linear velocity equals angular velocity measured in radians per time unit, per second, per hour, per week, per day, times the radius. Gives us linear velocity. Or if we know linear velocity and radius, then we can determine angular velocity. If we know any two of those values, then we can figure out the third one. There are lots of other examples that use radian measure, and I am out of time, so I'll shut up. I would pick out some problems and ask you to do them, but you've got homework problems, and that's enough. There aren't any problems from 8. There aren't any problems from 8.1. There are problems from 8.3, and there are also problems from 8.4, which I named 8.3 for some strange reason. I just typed it wrong. That's actually 8.4. Radian, that's spelled right, isn't it? Oh, you goofy thing. Alright. Sorry about that. I renumbered it. Let's stop there. And I'm out of time. So have as good a weekend as you can manage. I'll take a look at the exams and see what's up. And if we need to do something to adjust those, then we'll deal with that later. Questions? Problems? Supplement, folks, if you want to stick around, you can. Who talked to me? Matt came in late. Yeah. Is there anyone else who came in late? You should be able to find the exam. Here. So if you click on the exam, you'll need a password to start it. If you're not one of the people who came late and needs to take the exam, then you can go ahead and go. If you have any questions, let me know. Otherwise, I'll see you all later. I'm going to stop recording this, actually.